Alright, in this video we're going to be going over graphing polynomials. And just as a reminder, a polynomial is a special type of function that is of this form. A sub n x to the n plus some coefficient a sub n minus 1 times x to the n minus 1 all the way down to a sub 1 times x plus a0. Where these blue numbers, a sub n minus 1, are real coefficients and n is a positive natural number. So the important thing about polynomials is each of these exponents need to be positive natural numbers in the list 0, 1, 2, and so on. And the dominant term of a polynomial, aka the largest exponent that appears, is called the degree. And when we start doing further calculus, we'll realize that this notion of the degree is really important for determining important properties of the function. And for right now, even though we don't know any calculus, this degree also tells us some important things about what's called the end behavior. And this is a table that we started drawing when we were in class together, and here it is again, as I think it's a helpful way of putting all these ideas together in one place. So we have 4 different categories based on the degree of the polynomial and the sign of the leading coefficient, whether it's positive or negative. And in the third column is an example. So, for example, in the first row, if we have an even degreed polynomial and a positive leading coefficient, an example of such a function is y equals x squared. And notice y equals x squared, as x goes to positive infinity, as x gets really big, y continues to get really big. But also, as x goes towards negative infinity, aka as x goes towards the left on the x-axis, y continues to go up. Y goes towards positive infinity. And different things happen depending on whether the degree is even and the leading coefficient is negative, or if the degree is odd and the leading coefficient is positive, things like that. This table, definitely keep this down in your notes as it'll be important. And then the next thing we want to talk about is multiplicity. So if x minus a to the p divides a polynomial f of x, we say x equals a is a 0 of f of x of multiplicity p. So it's more than enough to say x equals a is a 0. Also 0 should be in orange as it's a definition as well. It's more than saying x equals a is a 0. It's how many factors of this term x minus a actually divide the polynomial, and however many factors that is, we say x minus a has multiplicity p. If p equals 1, the graph passes through that 0 kind of like a line. Intuitively, since p equals 1, locally the behavior of the graph at that point will just be a line. When p is even, the graph bounces off. It does either something like that, or it might look something like this, depending on which direction you're coming from. And if p is odd and greater than or equal to 3, then we experience this kind of wiggle happening, called an inflection point, that we'll see later on. All right. So let's graph the following function, y equals negative x to the 4 plus x cubed plus 2x squared, indicating correct x and y intercepts. So I already started the process of trying to factor this polynomial. I removed a negative x squared, or I removed a common factor of negative x squared from each of the terms, and then was able to factor this further as negative x squared times x minus 2 times x plus 1. So looking at this right away, we can already identify the zeros occur at x equals 0 with multiplicity 2, x equals 2 with multiplicity 1, and x equals negative 1 with multiplicity 1. So not worrying too much about multiplicity right now, we know that no matter what happens, our graph is going to have to pass through this point, and this point, right? We know that the graph is 0 when x equals 0, x equals 2, and x equals negative 1. Okay? And we don't know just without doing any kind of analysis, like, is the graph, as x goes to negative infinity, is it shooting up like this, or does it shoot down like this? And this is where the end behavior stuff comes from. So end behavior works by, we analyze the degree of the polynomial and the sign of the leading coefficient. In this case, we have degree is 4, so the degree is even, and the sign of the leading coefficient is negative. So that puts us in the category of the second row. So as x goes to negative infinity, f of x goes to negative infinity as well. So we know that the graph is going to go down. And similarly, as x goes to positive infinity, we also are told y goes to negative infinity. So the graph goes down again. Again, we don't really know what happens in the middle yet, but we know that these two things happen. Okay, now let's try to figure out what's going on as we get closer to the point, the origin. Okay, so we know that we eventually have to cross through this point because we have a 0, and this is x equals -1, and this is a 0 of multiplicity 1, so when we pass through, it's going to look, this isn't like, just to improve my picture slightly, it's going to pass through kind of like a line, right? And the same thing's going to happen at x equals 2, since this is a 0 of multiplicity 1. Again, these pictures are not perfect, but like we're not doing proper calculus yet. We're just trying to get a sense of what's going on. At x equals 2, similarly, we're going to pass through like a line. Okay, and we know to hit this 0 at x equals 0, we eventually have to come back down. And we are going to bounce back up because the 0 at x equals 0 has multiplicity 2. Right? So if we have multiplicity 2, this is the 0 that corresponds to bouncing back up. So this is kind of a, let me, connect the graph, make it continuous. Okay, this is a kind of a ugly sketch of like what this graph might look like. The important thing is we have the x and y intercepts. The y-intercept, I didn't explicitly state what it is, but it's, it's at the origin. We have our zeros, and we have the end behavior indicated. Okay, let's do another one. I also factored this one for you already, so we already can see the zeros, where the zeros are. The zeros of f of x occur at x equals -3 with multiplicity 1. X equals -2 with multiplicity 1. And x equals 1 with multiplicity 3. So let's include these points in the graph. So x equals -3 is over here, x equals -2 is over here, and x equals 1 is right here. Okay, those are our x-intercepts. How do we find the y-intercept, aka like when does the graph intersect the y-axis? The y-intercept is precisely this coordinate point 0, f of 0, right? It's the point wherever along this y-axis that the graph, what is y when x equals 0? So we just plug in x equals 0 and see what we get. F of 0 equals 3 times 0 plus 3 times 0 plus 2 times -1 cubed. Okay, but this is like 3 times 3 times 2 times -1. 3 times 3 is 9. 9 times 2 is 18, so this is -18. Okay, so it's down here somewhere. I didn't extend my axis to hit all the way down to -18, so we'll, it's down here. Not to scale now. Somewhere down there. Okay. All right, before we graph, let's talk about end behavior. I'm going to bring my graph down a little bit so I can continue this conversation in writing, not just saying it out loud. Okay. Okay, let's talk about end behavior. So for end behavior, we need to know the degree of the polynomial and the sign of the leading coefficient. So the degree of this polynomial, we say it's the largest exponent that appears, particularly in expanded form. So maybe your first instinct is, oh, the degree is 3 because that's the largest exponent that appears. But this is in factored form, not in expanded form. So it's 5. And if that's hard for you to see, maybe note that f of x is the same thing as 3 times x plus 3 times x plus 2, which is the same thing as 3 times x plus 3 times x plus 2. Oh, sorry, I forgot x minus 1 cubed. And when we expand x minus 1 cubed, I don't really want to write out all of the terms, but it's just x cubed plus some other stuff that I don't care about. And if we expand this further, the term that's going to contribute to the terms that are going to contribute to the leading term is x times x times x cubed. So this is going to give 3 times x to the 5 plus stuff I don't really care about. So that means that the degree equals 5, which is odd, and the leading coefficient is 3, which is positive. So we're in this category. The degree is odd and the leading coefficient is positive. The degree is odd and the leading coefficient is positive. Okay, that puts us in this category in the third row. So our function's going to do something like that. So as x goes down to negative infinity, the graph is going to shoot down. But as x goes to positive infinity, you know, it's going to shoot up. Like that. Okay? All right, I think we have all the information now to start graphing. Okay, so remember this is x equals negative 3, this is x equals negative 2, this is x equals 1. We said that x equals negative 3 is a 0 of multiplicity 1, so when it passes through, it's going to pass through kind of like a line. And x equals negative 2 is also multiplicity 1, so we got to come back down at some point in order to pass through it, and it also is going to pass through like a line. Okay? All right, and we got to go down, 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 down because we have to hit our y-intercept at some point. Remember, this is down here, way the heck down at like negative 18, not to scale. Okay, and I don't really know when it changes. We're not, you know, maybe it goes further down. We're not doing that advanced calculus stuff quite yet. But, you know, it eventually has got to come back up, right? It's got to come back up because we have a 0 at x equals 1. And this 0 at x equals 1 has multiplicity 3, so it kind of does like a wiggle, like this. This is like kind of a bad drawing, sorry, but I think you guys see the point. The important thing is that this is a kind of an inflection point happening here. These sort of pass through like a line, and our end behavior is indicated.